Thank you everybody for being here today, and especially for sticking around until the last day. I know a few of you are gonna leave right after the talk, so you might not stay until the closing remarks or the business meeting. I have two things to say. They are not here, but Marcello and Matteo, they did a great job, so I'm really, really grateful to them. Please do submit the papers for the volume. It's important, and we really look forward to receive them. And then, of course, I'm delighted to introduce Marcin Milkowski. So as you know, Marcin is the 2016 receiver of the Simon Award. Yesterday we had Jack Copland. The Simon Award is presented to junior scholars who have significantly contributed to the research fields of philosophy and computing. Last year we presented to Michael Scorla, the year before Gualtiero at Thessaloniki, and the year before Judith Simon, who's not here this morning, but she was also one of the receiver. So Marcin is associate professor at the Institute of Philosophy and Sociology of the Polish Academy, and is currently a managing editor of, I won't say the Polish name, but the Philosophical Literary Review. Oh, that sounds much better. And he has contributed significantly to the research in the field of philosophy and computing in many ways. I think perhaps you are more renowned for your volume, the 2013 volume on explaining the computational mind for the MIT Press. And I'm really glad you're here. We are very honored to be able to present you with this award, and we hope this is enough to tempt you to come back in the future years. So then, you know, it's like try to lure you into ICAP. So this is the award, and as I said, I apologize because I couldn't get the Italian engraver to produce Polish character on the plaque, but that's what you get. Thank you so much, Marcin. Thank you. And as for the others, you have 1 hour, 45 minutes, perhaps 50 for talk and then discussion. Thank you.
Thank you very much for inviting me and for honoring me with this prize, especially because of so many really good people having that. In the past, I don't feel I have contributed so much, but maybe I did without knowing. This happens to some people talking prose without knowing that. Okay, so my plan of the talk would be to talk about integration of models of cognition or mind. I will not define cognition or minds. I will assume that in cognitive science and cognitive neuroscience we have models that deal with that roughly. Then I will try to look at three modes, possible ways of integrating models, and then three strategies in trying to see how they fit with the framework that I'm trying to develop for explanation in cognitive science. This is a very much work in progress. I'm trying to understand how science actually works, and then see maybe there are some insights that might be used for a philosophical normative account of explanation by looking how people are actually using, how they are arguing about qualities of models, how they should proceed or not. So any remarks, comments, I'll really very much welcome. This is a part of my current project, which is supposed to take 4 more years, so I should have some time to integrate at least one comment that I received from this audience. Okay, so why integration? This is a very old idea, at least back to 73, when Alan Newell was tasked with writing a commentary to a conference. And by looking at how cognitive psychologists worked at the day, he got angry. He got angry because people were arguing, this is innate, this is acquired, this perception is direct, this is non-direct, and so on. So binary dichotomies based on very small pieces of evidence. So you do a special type of experiment, and then you interpret it to say something big, like there is a acquired ability to learn languages, or maybe it's innate. things like that, without really having a large theory that would explain what these things are. And he argued that you cannot really do that, because these are questions like playing yes or no question with nature. But you are presupposing so much without really knowing, you cannot win. So you should actually have a theory rather than just something like single disunified theories which look at single phenomena, which he called micro-theories, because these were only theories about those phenomena that took place when the subject was doing something very particular. There was no unity in explanations, as he said. So we need a theory. And his proposal, as is very well known, was to propose that we should study the architecture of cognitive systems. So we should have a structure, and we should build unified theories by simply trying to put those micro-theoretical explanations into this large architecture, so to see how it fits the whole picture. And that has led him to say that we might have unified theories of cognition. But notice that that is something like integration of those different single tasks. Unification is supposed to happen just because you gather them all together in a single architecture which is supposed to do everything. So instead of doing one single task, it is supposed to do 20 tasks, or maybe 200 tasks, or maybe 2,000 tasks, and then you will be done. You will have a unified theory. Now, I will be talking about integration. So the relationship of integration, what would be the relata? I think I will be very liberal. So you might have a internally integrated model that cannot be actually easily decomposed into two separate models, because somehow these components will be internally integrated. It might be integrated with some other models, or it might be integrated with some other representations, scientific representations. I will treat models as representations. Sometimes people talk about models as model systems that are represented by the models. So I will restrict myself to talking about models as things that do the representing rather than as model systems that are represented by the models. This is just terminology. Now, how do I understand integration? This slide is going to be a little bit packed, but the idea is that you can understand integration via notions of constraints. I don't see David Danks here because I have a little bit stolen this idea from his recent book. He has argued that there are ways of integrating multiple theories by applying different constraints. These constraints may be symmetrical or not. If you think that, for example, you're doing electric chemistry, then you probably don't want to deny certain fundamental physical things like law of conservation of energy, because it seems weird that not a fundamental theory denies something fundamental. Sometimes it might be symmetric because those theories do not seem to be in any hierarchical relationship. So the notion of constraint does not bring you, obviously, such a relation that as given in reductive relationships, which are not symmetrical, anti-symmetrical by definition. Now, the simplest constraint that you might have is simply truth constraint or logical coherence. If you want to integrate two theories, if one denies the other, there's something wrong. You don't want to, if you're not a fan of paraconsistent logic and you're trying to use standard frameworks, you probably don't want to have any contradiction in your model. So you don't want to deny something that has been established by another model or something like that. So it's a very simple constraint, but it's also very weak. things which are completely logically independent are not truth constrained, but they are also coherent, because their truth value is independent. So it's a weak constraint, and it doesn't give you real integration. If you simply have 20 theories connected with conjunction, and they are completely logically independent, well, it's not that they are contradictory, so it's fine. It seems to be integrated, but very weakly. Someone might be tempted to say mechanically, but given that my preference for mechanisms, I will not say the word. So I will talk also about mechanistic constraints. Those mechanistic constraints would be constraints related to things that are mentioned in mechanistic explanations, or explanations that refer to complex structures composed of activities and entities, as Carl would have it, or parts and operations. There are different terminology used by different proponents of mechanistic explanation framework, but the most important thing is that you want to have the same entities if you want to integrate models. What would that mean? For example, you are supposed to assume that there would be the same components, maybe at different time scales, described by different models. So maybe at the same time scale if it's just like pieces of a single puzzle. For example, a model might explain an earlier phase of some computational processing, then it's very easy to see how those things might be connected in a row. Okay? They would refer at least partially to same entities and activities. Maybe not entirely, but at least there will be some part which is a common core of those things. So now I'm talking not only about logical coherence, but there is some consistent way of referring to the same core of things. And to be more precise, you might have different types of constraints that would require you to be actually referring to the same entities. That might be, for example, spatial and temporal features. If you know that a certain biological thing has certain shape, it should fit with something else that has a corresponding shape. If those two models deny, they posit different shapes, it's not actually a logical contradiction, obviously, in an evident way. At least you have to do some virtual information extracting to get at that, but you want to have the same kind of or corresponding shapes in both models, things like that. And so there would be spatial temporal features that would actually constrain you into more and more talking about the same things. So basically, at the back of my head, I have the idea that integrating is satisfying multiple constraints, which would give you coherence of integrated representations, but those would not be just merely logically consistent representations, but they would have some common core, and that would give you integration. Okay, that's how I understand integration. Now, I think that there are three major strategies in integration happening right now. Maybe there are more, so there is nothing magical about number 3 here in cognitive science. The first is, as we have already heard, cognitive architectures, already introduced by Alan Newell. Then we have interfaces, and then we have some empirical constraints. That picture is supposed to prime you if you know Rube Goldberg machines. I will explain that in a minute. Okay, so what's the recipe for integrating via architectures? You build a general outline, a blueprint for a cognitive system, and then you try to rephrase existing models to match the architecture. There will be trade-offs, because sometimes, or actually almost inevitably, you will have to simplify. You will sometimes have to just have proofs of concept. If you look even at very advanced models proposed today, like SPAWN, 2.5 million artificial neuron model of the brain, which is supposed to model neural assemblies rather than individual neurons. This is at the same time a cognitive architecture, but to implement multiple tasks on this architecture, actually, Chris Eliasmith and his collaborators had to simplify a lot multiple explanations that they have used. And people who work, for example, on tasks connected to executive functions, which are supposed to be responsible for intelligence, general intelligence, posited for explaining fluid intelligence in solving intelligence tests like Raven matrices, they say it's definitely not credible that we do it this way. But the point of Eliasmith was to show that at least in principle it's possible to have something like that. So these are just proofs of concept. These are not finished and full-blown explanations yet. So you have to get a lot more into the architecture to have that. But the question is, when? I mean, this is very difficult to get existing work and to rephrase it completely and even add something to it. So basically there is already an overhead connected with rephrasing and building the architecture, and then you need to fill the gaps in previous models, and then maybe your architecture will have some problems because in SPAWN, for example, there is a very minimal notion of work in memory, and that's very bad when you want to have executive functions. So it has to be a proof of concept. Sometimes people think that the way certain tasks are integrated with cognitive architectures is simply superficial data fitting, and people from ACT-R community, ACT-R is another more classical architecture that is supposed to integrate especially insights related with response times. So it is able to model our performance in terms of temporal execution. But the way it's done seems to match the experiments, but not so much deeper structure of things, because you simply know already the timing and you simply give the values. The model works this way, but it seems to be overfitting. So it might be a problem. And my favorite problem is that you might create monsters. And the monsters will be understood in a technical sense of the word. Namely, there's a picture coming. This computer is slow, takes its time. So these considerations about monsters have been proposed already in Thessaloniki by Ioannis Fotsis. So it comes from previous IACAP. And let me see. This is what I mean by monsters. This is a complex machine that integrates multiple things: a thermometer, a clock, 2 lamps. It's basically Rube Goldberg machine for doing something very complex. It's not very clear what it does, but it integrates a lot of things. Why is it a monster? Because it retains all these artificial shapes which are not really necessary. Okay? You don't need those things. It makes it look funny, but it doesn't work properly. So this is the intuition. Let's go from intuition to some serious philosophy. So what I mean by that is that not all coherent representations are good scientific theories. You might say you want to have beautiful theories. That thing was not beautiful. But of course, beauty is somewhat aesthetical criterion, and I think we can go better. We can do better than that, because I actually have a preference for ugly things like that. So I think this is this tells you about disunification. So you might have disunified theories which are integrated. They do something together. It's not that they're disconnected. But when connected, they are not really very coherent. They are ugly. They are bad. They are just mechanically glued together. So the more monstrous the representation, the less it is unified. And now, how to understand monstrosity? Watts proposed that monstrosity is the level of conformational disconnectedness. So if you do not have connections between the evidence that would confirm your model, different parts of it, you would get monstrous things. Intuitively, if some evidence does not influence all of your model, just parts of it, it seems that it is to some degree monstrous. Of course, if it in the limit, it will be totally unified. It will be like Otto Neurath's idea of unified single law that can predict everything and everything is relevant to it. So of course it comes in degrees, but there will be certain disconnected things that do not seem to be very well. What was that? Oh, it didn't want to show the proper definition. There is a proper definition, which is on purpose very small, because I won't read it. The idea is that you can define that on the level using logic and certain additional ideas about entailment and things that are really entailed and not superfluous. So basically you have to first you have to normalize your theory so that things like P or P or P or P would be reduced to something less redundant, or P and P and P and P. So those redundant parts would be removed if they can. And if you have two theories or two sets of propositions which are conformationally disconnected, there would be no true proposition that follows both from one set or the other, and they will be also probabilistically disconnected, which means that they will not be composed of tautologies here, and their probability will not depend on one another, and no atomic proposition would be contained in both. This is his basic idea. There is more. I don't want to stay on that level, because unfortunately it's not directly usable for architectures, just because they are not expressed in the language of predicate calculus or this kind of logical medium. So you have to first redescribe it to have this kind of representation, which might be sometimes very difficult to do. So probably you could approximate this, especially for these non-propositional models, which talk about networks and so on. Of course, they could be described, but descriptions would be pretty difficult to produce. You might simply try to measure that conformational disconnectedness by looking at what you already have, and what you already have usually is certain ways of validation or checking whether the model matches reality, which is somewhat quantified. And you might try to see whether there is statistical independence between validity of different parts of the system. Or maybe you could try to do some analysis. Maybe there is some mutual information between parts of a system, things like that, which might be directly achievable for at least some models without redescribing them logically. It doesn't really matter for me. I think some way of doing that might go beyond simple intuitive sense of what monsters are. But of course, if you know you have monsters, sometimes you don't really need any deep way of measuring monstrosity. You want to fight monstrosity rather than to measure it. And let me just show one attempt, which I don't think is the most important one, but at least shows that in the cognitive architecture community, you have people who are deeply concerned with the problem and they try to solve the problem. So there is a model proposed by Kasimatis that has the approach which is called common function through multiple implementation. Kasimatis thinks that there are just a couple of cognitive functions that compose all cognitive functioning. I don't necessarily have to believe that, but the idea is that you can be, if you are able to do some forward inference, if you are able to formulate subgoals, if you can check identity of objects, and if you can represent counterfactual worlds. Oh, I have 4, it should be 5, whatever. You can compose out of that multiple other cognitive functions. These are implemented as specialists, not as modules, that communicate through so-called focus of attention. So on a picture, it should look like that. If you have a modular architecture, it would have completely distinct components. Some of them might be responsible for search, some for vision. There might be a neural network somewhere, there might be rules somewhere, space memory somewhere, and temporal constraints separately. So you have, say, 6 separate components that have to communicate with one another. In polyscheme, there would be multiple specialists that all have different aspects of these, and whose locus of control is transmitted by assigning this focus of attention. Okay, so the idea is to have this integration not via building separate isolated modules, but by trying to get a unified picture of what is a possible primitive operation which is responsible for, whose combinations are responsible for implementing multiple cognitive features as individual steps, and then you might connect them in chains and branches and so on. So that's the idea, and I think the most important idea here is that instead of trying to get as many tasks as possible to be fitted to data, the approach is to try to find some common underlying unity behind it so that it would be simpler. It's not necessarily more successful because there are not so many people working on that, and maybe there are some problems with positive functions, but I think that shows that people are deeply aware that there might be problems with models that are simply very disconnected. Let me go to another strategy, which is building interfaces. If you really want to have standalone or modular things, then you have to establish data links. So different computational subsystems may simply use their input-output data, or you might have something a little bit more interesting. You might have communication in hybrid architectures. So in the first case, you might have subsystems. I don't think there is much theoretical gain for a theorist. Let me give you an example. LF Python, this is a software to describe local field potentials using Python, and Neuron software which is used to simulate neurons. So this LF Python describes an object-oriented way the biochemical, bioelectrical features of local field potentials, and you can compute them, and the results of computation might be fed to neuron software. There is nothing really special here because it doesn't necessarily show that there is any deep connection between these features. You have to know them beforehand. You simply compute them separately, then you join them, and that's all. So these interfaces, although very important to make modeling work, are as important as modules in MATLAB. They are very interesting, very, very useful, but don't give you integrated theories. So that integration is not theoretically significant. Whereas if you have a hybrid architecture, it might be theoretically relevant. For example, if you believe that Clarion is a very good architecture proposed by Ron Sun, it would posit two layers of representation, implicit and explicit. And here is the very general scheme of that architecture. And if here are those interfaces in arrows. You have explicit representation, action-centered, connected with action-centered implicit representation. And non-action-centered explicit representation is connected to non-action-centered implicit representation. And these are also connected together. So you have to posit some interfaces, some ways of linking those data. And that's theoretically quite difficult. How is this possible? How would you link those? Would you need to have implicit representations being transferred between explicit and implicit? How would you do that? I mean, the arrows actually do not show you the complexity of the task that is before someone trying to have those really different architectures. Because how you decide to transfer data between those two parts is significant and important. Because this is supposed to correspond to how the mind works. So this is not only your insight about those two different kinds of representation. It is supposed to match the brain. And it's very difficult to operationalize, very difficult to check whether your insight is true. So it is even if it's just a small arrow, it is a very important arrow that actually bears a lot of theoretical weight in this model. So it has to actually, it's a misleading picture because that should be the main part here. The rest is just as in other architectures. Those parts between those two kinds of representations represent the real theoretical idea. And more than that, not only it's very difficult to say how it's connected to the brain, building architectures or building models that talk about data or information transfer in the brain are difficult just because the brain might be complex. And even if human brain has very complex network, even for simple organisms that we already have a connectome for, it turns out that it's really, really difficult to understand how those things work. So interfaces might turn out to be a way of integrating things that actually require deeper thought to understand what's the unity behind it. Because the current interconnected loops and lack of hierarchy in organisms that we know that they have certain connectome show that our current methods are not sufficient. So there is a disunity. So let me go to the last type of constraint, which I call empirical constraints, like Miller magic number 7 plus minus 2. The idea is that you are integrating your model with known principles. So basically, you are not getting some other model. You're getting on board certain knowledge that you think is relevant because it's justified experimentally. And I think it's theoretically critical because it constrains theorizing, speculation, and cognitive science. So to start with Miller magic number, Newell and Simon posited that the short-term memory cannot have more meaningful chunks than 7 plus minus 2. So you cannot posit infinite short-term memory in your model. Then in connectionist simulations, a rough approximation of 100 operations per second was used to say, if you have more, it's not brain computationally feasible. It's too much. It's not credible. It's not plausible. So basically, by integrating those constraints, you are supposed to gain some biological or empirical plausibility. There are certain very obvious things. Location addressable storage as simulation of biological memory is also biologically very implausible. If you would also have a model of human vision and then would assume just one pathway, we know that there are at least two, somewhat connected, somewhat disconnected, but saying that there is just one, that would be a huge idealization that should be in some way justified. So you can ignore those, but you have to modify your idealization in a model. So of course, you might say, well, hold on a second. This is not really integration between models. You were supposed to talk about integrating models. This is not integrating models. This is right. This is integration of theoretical insights from empirical evidence, neuroscientific evidence, sometimes more or better justified or confirmed. But I think it is still some kind of integration because it satisfies my kind of getting more coherent representation of cognitive functioning on board. The problem is that this is more art than science. Which constraints you are supposed to take on board is basically, well, this is your benevolence. You do not have to. Why 100 operations per second? If you think that it's not so important, or that maybe that neurons do much more, why not? The ways of implementing that are also contentious. How would you implement this 7 plus minus meaningful chunks? It's pretty obvious how you do that in symbolic architectures, but for connectionist architecture, it's no longer so obvious how it would match. Would you need to have some modules in your network? Inputs? Layers? It's not straightforward. There is also a danger of overgeneralization. If you would believe Miller, you might also posit that all short-term memory is like that. But we know that the phonological loop has more, has bigger capacity than short-term memory. So if you would take that on board, you wouldn't be able to have a model of phonological loop, which would be premature optimization of your model or premature way of tweaking the model before you have evidence from other domain. And generalizing from one domain to another is a very common thing in cognitive science. But it might seem that this is the way people are building biologically plausible simulations. they take on board multiple constraints. They try to say why they are important. For example, Chris Elias-Smith would say that having a dynamical model of a neuron is critical because neurons are not mere points in a network. They activate in time, and their time-based activity gives you coding, rate dependent, and so on. So those codings in time are impossible to be modeled in any other way. So that seems to be, unfortunately, shows you that modeling is still very artsy. So what would be the take-home lessons from that overview of the field? I think that if you look at how people are doing the models today, I think the days of splendid isolation, building those isolated models, even if you are being charged with the objection that you are focusing on very special tasks, as yesterday a paper about poverty of embodied cognition did. Those theorists were charged with focusing on sensory motor tasks, basically. It is assumed that everybody would say, yeah, this is important. You don't charge someone with saying, you're doing what you're doing. Because, I mean, you would say, of course I do what I do. I'm looking at motor things, yes, I do that. But the charge is important because you are not supposed to do that. You are supposed to build integrated knowledge. If embodied cognition is supposed to give you unified view on cognition, as Larry Shapiro has argued, then it would better integrate everything in a unified fashion. So splendid isolation, also splendid isolation between cognitive science and cognitive neuroscience is gone. So people try to do that. But cognitive architectures, contra Newell, are not the only way to integrate multiple insights. I think the default way of doing that is via empirical constraints. Cognitive architectures are just one way of trying to get a unified vision, and they are not without problems. Some forms of integration, even in cognitive architectures, if you try just to fit the data, if you have multiple parameters, as you do in Actar, it's very easy to fit the empirical data, so it's not a very big deal if you fit the empirical data. So only some forms of integration are theoretically relevant. And unfortunately, one huge problem is that empirical underdetermination is still a huge problem because there is no way to confirm or disconfirm most of the models that we have. And for all the theoretical insights that we have about indeterminacy of computation, we are not even there to say what kinds of building blocks are there, because it's very difficult to say that. So there is a huge gap between theories and phenomena. And it's also unclear which constraints should be taken, which ones are really important and which not. So basically, the limitations of integration is that if you try to integrate too much and too quickly, you might create monsters. The questions of how to transfer control in such architecture are still very much open, and it's very hard to say how they should be integrated. Those interfaces might be built initially instrumentally, but then if you have a working simulation, maybe you should make them biologically realistic, but it's not clear if it's even possible. And constraints may be contested. Possibly they might be also irrelevant if you're doing artificial intelligence. If you're doing artificial intelligence, imposing the short-term memory constraint is completely, why should you? I mean, you might try to run with a huge ball connected to your leg, but it's not required. So there might be a gap, growing gap between artificial intelligence and cognitive science, just because the more constraints from empirical data you have, the less suitable ideas you might have for developing general artificial intelligence that goes beyond certain human capacities. So, just to conclude, I think integrated computation models are here to stay, but we still don't understand how they work. The integration without unification, which I did not talk about much, but that was in the background, may lead to monstrosity. Complex models are easy to fit, but simple models are too isolated. So either you're doomed or you're doomed, but in a different way. And unfortunately, there might be a reason why cognitive science people are not so much interested nowadays with AI, just because there is a growing gap between those two fields. And the lesser citations in cognitive science journals and to AI papers might be understood in terms that these people are busy with doing different things. But this might be, of course, contested. Thank you for your attention.
To be fair, I don't know a lot about the area that you're working in, but as you spoke, the thing that kept coming to mind to me were software patterns. And these are techniques that are used to build complex pieces of software. And so I'm wondering if you're aware of them, and if not, I would like to make the suggestion that you might take a look at them to help solve what I think your problem is.
I think, this might be a solution if you're building AI system. But the problem is that the structure of Octar, for example, is built for theoretical reasons this way and not another. So trying to get, in software engineering, a good way of getting rid of redundancy is to generalize, parameterize, get another class doing two things at the same time, okay? You cannot do that in psychological models so easily, because sometimes there are reasons to see that these things are separate because they fail separately. Because you have lesions and these are different functions, so there is a dissociation. So you have a structure, a blueprint is usually based on certain data that, like two visual pathways, you might generalize have one. But in reality, you might have blind sight just because the two are separate in reality. So it's not so simple that you could look at the structure and simplify. Of course you could, but then you might create theoretical artifacts. You would aggregate, you would lump things which are in reality disconnected, and sometimes you might be interested with these disconnections. That's why it's not as easy, but of course, in certain ways, it might be used.
Thanks, Marcin. It was very, very helpful. As you may know, I'm also in favor of unification in cognitive science and neuroscience. But I'm just not sure if you emphasized enough, and perhaps you did, and I was daydreaming, but when you're talking about the architecture as a platform to achieve integration with unification, I'm just wondering, because we have so many different architectures, and we can start debating about what exactly constitutes an architecture, but you've got the ACTR, you've got Clarion that you suggested, you've got the NEF framework that Elias Smith, I'm not sure if he still calls it NEF, etc., but it seems to me that those architectures are very restrictive in an important sense, and then by trying to integrate through committing to a particular architecture, and if this architecture is faulty or makes very strong assumptions that you don't want to buy into, it's restricting a priori the theories that are actually trying to integrate with other theories.
Yes. I mean, I might go longer, but the thing is, when you have a theoretical framework that is used to integrate your insights, obviously that theoretical framework is used beforehand. And you have to justify that, of course. You don't have to be dogmatic about it, but you cannot do much without changing the architecture or changing the theory. This is what you accept. So yeah, that's a problem, but you might see that as a feature, not as a bug. Because this is supposed to work this way. We have too much freedom when modeling.
So I have two points. The first is the last bullet here. You say explanatory model of psychological phenomena might be irrelevant for AI, but in the past, these were very relevant. For instance, the model of memory, which is a basis of the hypertext, has been very successful, and the web is based on this, is the notion of hypertext. It is a psychological model. And more precisely, the model of memory on which are based semantic memory is very useful, because today knowledge representation technique, schema, RDF schema are based on this, and description logic are also based on this, and object-oriented programming are based on this. So they were very efficient in the past. So I'm a little bit surprised with this. I don't know what will happen in the future, but this explanatory model of psychological phenomena were very efficient. So this is the first one. The second point is about the notion of model. So a model is, etymologically, it's an intermediary things between you and the object you are studying. And so the role of the model is very pragmatic. So if you build a too general model, it's very difficult. So because we are in Italy, I would like to mention a very nice text. Maybe you know, the Italian know, from Italo Calvino. I think it was in Mr. Palomar, I'm not sure, the model of the model. And it's very interesting, because he said, okay, it would be very convenient to have a model. So it's, he said, I would like to have many models to see many things. And then he discovered that a model is like a prison, because he sees everything through the model. So it's restrict his view. And then he tried to extend the model, and then he has a very general model of everything, which is too general. And I think this is exactly the problem with model. I don't want to say that models are useless, on the opposite, but I think you have intrinsic limitation of model when they are too general.
With the first claim, I totally agree. I have a very weak statement here. This is just might be. I'm not saying they are. There is a class. At least some of them might be completely irrelevant. Some of them might be relevant. Sometimes those constraints might be important because you might be constrained in resources, and seeing how limited brains do that might be useful, but sometimes not, because these limitations would not be connected to energy or things like that. They might be just haphazard, just because the brains are like that. So I'm not saying that there will be inevitably a gap, but I think the gap is growing, and it's interesting to see why. So if you look at the citation patterns show you that artificial intelligence journals are less and less referred to in cognitive science journals, and vice versa. So these fields are going a little bit apart. I don't think they should go very much apart, because the techniques from one field might be relevant to one another, but sometimes people assume that they will always be. And as for models, it's pretty obvious that if you could have the same with a map. Borges' story about the map, which is as detailed as the territory, is as useless as anything. So you have to simplify, you have to idealize, you have to reject a lot. But if you have rejected too much, it won't show you anything. So there is a certain trade-off.